Okay, so let's look at an example. Sum n equals 0 to infinity of x minus 1 to the n over 3 to the n plus 1 cubed. And this is an example of a power series centered at 1. So you don't care how mad the CNs are, you're looking at the x minus a to the n piece. So this is a power series centered at 1 because a is 1 in our example. Okay, so remark, again, a power series defines a function f of x equals sum n equals 0 to infinity Cn x minus a to the n. So you give me an x and I can plug it in, replace it in that series formula. Fundamental question again. What x can I plug in here? What x makes sense to plug into this series? So if I'm going to tell you this thing is a function, you have to ask me what is the domain of this function, i.e., for what values of x does this series make sense or converge? So we're going to look at a theorem now that's going to answer this question. Okay, so theorem. For any power series, sum Cn x minus a to the n, there are only 3 possibilities for describing the values of x for which the series converges. Possibility 1. The series converges only for x equal to a. So we know the series always converges at x equals a. The first option is that that's the only place where it converges. Second option, so that's the first case is the worst case scenario. Here's the best case scenario. The series converges for all x in R. So for every number, every real number you can think of, it converges. It makes sense. You can plug any x element of R into your power series. Third option, there is a positive R such that for absolute value of x minus a less than r, as in for an x that's r away from a, less than r away from a, the series converges. For absolute value of x minus a greater than r, the series diverges. And inconclusive on the boundary. So inconclusive when a is exactly r away from x. Okay, so in pictures, what does this mean? Well, the first case means if we draw the number line and we mark A, then we highlight in yellow where we converge. It's literally just at the point A. In the second example, we can highlight A again, and where do we converge? Well, we converge on all of R, so we highlight the entire real line. Now the third case is the interesting case. We mark down A, and then we have to look R to the right and R to the left. Those two don't look the same, but just imagine they're the same length. then we know that we converge inside this bracket. And we don't know what's happening at the edge case. So when you're exactly R away from A, we're not sure. You have to check those cases individually. But if you're outside there, this orange means that we diverge. Okay, so I'll fill in those two boundary points. The blue dots we don't know, but for the yellow inside this open interval, we know we converge. If we're outside this interval, we know we diverge. And on the boundary cases, again, we have to check them individually. So this summarizes the three possibilities for describing the values of x for which the series converges. So your power series either converges just at A, converges on every point of the real line, or it converges on some interval. Intervals centered at A, with potentially the endpoints or not. So it could be open interval, it could be half open interval, or it could be closed interval. But it's always centered at A. So this theorem leads us to the following definitions. First definition: if such an R greater than 0 exists, as in case 3 in the previous theorem, for a power series sum n from 0 to infinity, Cn x minus a to the n, then we say R is the radius of convergence. Of this power series. Okay, radius of convergence. But if we have, as in case 1, so if the series only converges at x equals a, we say that the radius of convergence is 0. And if you think about the picture, this makes sense. It's a 0-width interval. And then what do we think we say for the second case? Well, if the series converges for all x element of R, we say the radius of convergence is infinity. Okay, so R equals 0, R equals infinity. Second definition: the interval containing all x such that the series converges is called the interval of convergence. So, interval of convergence. In case 1, the interval of convergence is just a single point. It's just a set containing A because you don't converge anywhere else. In case 2, the interval is all of R. So the entire real line, minus infinity to infinity. Now in case 3, it's a bit more complicated because we have a few scenarios. So in case 3, remember we have this R greater than 0. So the interval of convergence is either the open interval A minus R to A plus R, so you don't converge on either endpoint, or you converge on the left endpoint, and not the right, or you converge on the right and not the left, or you might converge on both. Okay? So in this third case, we have 4 possible options for how the interval of convergence is going to look. Okay? So some people call the radius of convergence for short ROC. You might see this in questions, and the interval of convergence can be denoted by IOC. An example where we can determine the radius and interval of convergence. Well, we're going to keep coming back to the geometric series. Now we know this converges if and only if, so these are the only points where it converges, absolute value of x strictly less than 1, i.e. the radius of convergence is 1, because we converge for all x between -1 and +1. And the interval, just to express that concretely, the interval of convergence is the open interval from -1 to 1. And in line with what we said before, this is centered at 0, which makes sense because this power series we're looking at is a power series centered at 0. It's x to the n, which is the same as x minus 0 to the n.